So let me go and start reviewing here. Okay. So one of the things that we've been looking at here is that we've been looking at, we were looking at how mass and energy are related, especially when we start to do, converting mass into energy and energy into mass. And we looked at two examples. The first example that we looked at is we looked at the unstable bound states as well as bound states that are stable. So when I look at this thing here, I want you to think of this as a flow chart so that and then we interpret what the flow chart is. So what happens here is that you could imagine that I have two particles. For simplicity, let's say that these are two charged particles. In other words, I have a positive charge and I have a positive charge. And what I'm really looking at is I'm looking at the nucleus, for example. So I want to form a nucleus and I have two pieces of it that are charged. So the fact that they're positively charged, that means that they repel each other. So what do I got to do? I got to come in and I have to do work. I have to do work. And then I do work, and what do? I bring them so close together. I get them close to within what are called 1 to 2 Fermis, and then the strong nuclear force takes over. So now I have two forces that are working against each other. There's the electrical force. There's the electrical repulsion that are pulling these guys apart or pushing these apart. And then there's the strong nuclear force that are pulling these guys together. I have two competing forces. That is true of almost every single bound system that occurs in nature. So the flow chart is then, if this electrical repulsion is stronger than the strong nuclear attractive force, I form an unstable bound state. And we talked about this like a spring Velcro type system. And so so the work that I do, what does it do? It increases the overall energy. In other words, the work increases the internal energy of the system. So then it forms an unstable bound state. So what does that mean? That the energy that I did here is not going into kinetic energy, because I'm going to say that the particle that's left over is at rest. So it has no kinetic energy. All of that energy went into this mass energy expression. And I say, be careful what the book says here. So when I look at this bound energy state, it has this bound mass. So because I did work, the energy had to go someplace. So a lot of textbooks will say what? That the mass increased of this thing. And I'm saying that's not true. That the energy has increased in the overall system. We don't measure mass per se, we measure energy. And so what happens here is that because this is an unstable energy state, I look at these energies, and these energies eventually decay. So a measure of these energies is essentially after the products decay now. And when they decay, we have a combination of rest mass and kinetic energies. So when we go to look at how this object, in quotes said gained mass, remember mass is an invariant, how it gained mass energy, we measure the kinetic energies of its products. And so when I measure this, we say that the system had a change in bound rest energy. This bound rest energy is then, you'll see that the bound mass energy is higher than the constituent masses. And the difference is the kinetic energy. So the real big takeaway here is that when we measure mass, and every day, we're really measuring mass energy. And one of the examples that I gave last time was the proton. So let's think about you. As people, you are really made up of protons and neutrons. The electrons they do play a tiny, tiny role, but it's so insignificant that we can ignore it. So if you look at the mass of the protons and the neutrons, 90% of it is in the form of something other than the mass of the quarks. So in other words, let me say this one more time. When you go to measure the mass energy of a proton and neutron, 90% of the proton and neutron is in the form of kinetic energy. And it's a complicated kinetic energy. The vast, vast majority of it is in the kinetic energy of the gluons, as well as the potential energy of the strong nuclear force between the gluons. These particles are massless. So because of that, that means that your mass, so if you weigh 100 pounds, 99 pounds of your body is effectively not mass, but mass energy, which is kind of trippy when you think about it, because you're kind of thinking like, yeah, this is how much bulk matter I have. Think again. Relativity tells you that's not true. 99% of your energy is effectively kinetic energy. Now note, it's a little bit more complicated than that, but it's a very, very good approximation. So the way we looked at this as an example. And the example that we looked at was thorium decaying to radium and an alpha particle. Now, if I looked at Gamma's model of alpha decay inside of thorium, we have a bound alpha particle that's bouncing in this potential barrier. So when I say, what is thorium? A good picture of thorium is this green curve. That's the potential energy or the potential of thorium. This is a better picture of thorium than, let's say, this picture right here. And what you're seeing here is that the true quantum mechanical description of what do we mean by an unstable particle is that this alpha particle that's bouncing around inside this barrier, the fact that I have a finite distance means that it can actually tunnel through this thing and get out. And that's purely a quantum mechanical thing. Special relativity does not allow that to happen, but it does happen in quantum mechanics. Why am I telling you this? That this is the definition of what do I mean by an unstable bound system. If the potential barrier is not infinite, then that means eventually that particle will go through that barrier or tunnel, as we say, quantum tunneling, or in this language, it's in a bound system that's unstable. Okay, so then we talked about, so if I look at this flow chart, I do the exact same thing. I go into the nucleus and it says I got a radon and I got an alpha particle. What do I know about them? They're both positively charged. So what do I got to do? It's unstable because I got to do work to bring these guys in together. As I work them to bring them together, the system goes to a high energy state. So my work increased the overall energy of the system, which is internal energy. And then if I form a thorium that's at rest, it has zero kinetic energy. When it decays, then the radium and the alpha particle then go back to back because it's now repulsive. And so what you're seeing here in the system here is that when I go and I measure the kinetic energies of this radium and alpha particle, and I compare it to the mass energy increase of thorium, because it's unstable, it's exactly the same difference. And so a lot of times people are going to say that thorium increased in mass. Of course, we're trying to be careful with the language. Thorium did not increase in mass. It increased in mass energy. And therefore, the measure of those kinetic energies is exactly that mass energy increase of thorium. And you can measure that, and we do. And one of the things that we said about nuclear bombs here is that how do you form these things? Well, uranium-235 atoms are highly unstable. So you have to look at, what does potential energy mean? It's the work required to bring two constituents together. And when you do that, and this thing now decays, you find that mass energy, right, this delta M bound C squared, is essentially the energy used to give kinetic energy to those constituents. They're one and the same. And it's this release of this electrical energy that now really creates the explosion that we've seen. Then we went to an stable bound state. And the difference between a stable and an unstable was the attractive and the repulsive forces. So as long as we can get a fairly long bound state, it doesn't have to be forever. And the reason why that is that quantum mechanics tells you that kind of thing happens. So it's not really part of relativity. But the way I try to get you to visualize, and remember, the goal of theoretical physics is to write down the potential function of the universe. If you can do that, you, in theory, can explain anything. But note, we'll never be able to do it because the world is way more complicated than that. And what you find here is that if I do a potential mapping, and what do I mean by a potential mapping? Well, this here is a gravitational potential mapping. And what do I mean by gravitational potential mapping? You could imagine that you're going to walk or run, whatever you're doing. And as you're running and you see, what you do here is that you see this hill in front of you. What you have done is that you have actually seen the gravitational potential, not the potential energy. It turns out that energy requires two things. Potential only requires one thing. So you see the shape of this thing. And what we know here is that now that we've seen the shape, now if I put an object in that space, this potential space, then we could talk about something having high energy, something having low energy. And then the language is that if I want to take this object 1 and I want to take it to location 2 here, I know that if I want to get that object to the top, we then come in here and we go like, okay, I know I have, if I really want to get it to the top here, I need this amount of kinetic energy to get all the way up the top to there. And when I get all the way up to the top to here, we're saying here that this tells me how much gravitational potential energy I gained as I go from point 1 to point 2. So this potential mapping tells us when I have high energy, when I have low energy states in terms of potential. Now that becomes super important when you're trying to form bound states. So for example, we started talking about hydrogen. Hydrogen is a bound state between a proton and an electron. Now, according to the principle of relativity, I could take the viewpoint of the proton or I could take the viewpoint of the electron. So if I stand right on top of the electron, what is the electrical space that the electron shows? Well, it turns out that it looks like this. And if you've had 4B, you know that the potential function of a point charge is proportional to 1 over r. So this curve right here is 1 over r. Now, so all I'm telling you is that that's the shape. So when I think about this shape, this is the shape I'm thinking about right here. I'm not trying to get you to understand why the shape is this way, because nobody knows. That's what nature tells us. But this shape you can kind of relate to in everyday situations. So now what happens? What happens then, if I formed a bound state between a proton and an electron, the electron attracts the proton. So if I'm sitting on top of the electron, then it's the proton that is being attracted to the electron. So what happens? This proton slides down this electrical potential energy here. And so what do I call this? It's a high energy state, and it goes to what? A low energy state. And what I mean by that is because if this is 0 and this is a negative number, I'm going to a more negative number. I'm going from 0 to a negative number, which means that this is less than 0. So in this case, 0 volts or 0 potential tells me that that's the high potential and that's the low potential. So in the language, what do I mean by this? Well, if the constituent started at a high energy, why do I know this is a high energy? Because a bound state implies that you're going to a lower energy state. Then that means that the bound state of hydrogen must be a lower energy state. So if I start to think about this, what this tells me here is that it tells me this. So a bound state okay, what's going on here? Let me see if my pen works now. So a bound state is a lower overall energy. Okay, it's a lower overall energy. That means then that the energy of the proton, which is mpc squared, and the energy of the electron, which is mec squared, that this is the higher energy state, and it now goes to what? It goes to the bound energy, and this bound energy is in the mass of the hydrogen atom. And when I look at this, this now forms a lower energy state. So the only way this could be true here is that as I transition, right? This is a transition. As I move from this higher energy to this lower energy, that means that there must be something, some energy that must be sort of like taken away here. So what I mean by that is that this guy, when I say lower, I really mean a lower mass energy state. That's a lower mass energy state. And the only way this could be true here is if the energy of the proton plus the energy of the electron, the only way this could be true is that there's something subtracted from this thing. Right? There has to be some subtraction that goes on because we already said this is a higher, that's a lower. And this is what we call the binding energy. You know, this is a really beautiful concept in quantum mechanics. It really is. There's some really, really, really cool stuff that goes on in here. And so, you know, I'm not going to go into it any more than that. I'm going to leave it right there. There's no way I'm going to walk into this thing. So what you're finding here, so what do we really call the binding energy? So the binding energy so that means E of binding then must be the energy of the constituent minus the energy of hydrogen. And so what you're seeing here is that if this thing is produced at rest, then this becomes the mass of the proton, the mass of the electron, the mass of hydrogen. There's a difference between these two. And this binding energy is literally the reduction in the rest energy of this bound system. So there is a difference between these two. And here's what's really, really amazing here. Okay. And what you find here is that something really beautiful happens in quantum mechanics. This thing works so well. Okay. This thing works so well. So this is the binding energy. And this binding energy is exactly 13.6 electron volts for hydrogen. It's exactly that. Now, here's what happens. So if you were to look in practice, people have actually formed bound states of hydrogen. So in practice, one can form hydrogen. And the way they form hydrogen here is that they literally take two charges. Okay? Right? They have two different animals, a positive and a negative. So here's my positive, here's my negative. And what you allow them to do is that you allow them to form hydrogen. So if you take them just right, what you're going to find here is that afterwards, you now have hydrogen. Let's not do it this way. So how about if I do this? So you now have a bound state of hydrogen, and right, so now you form hydrogen. And in this process, when you form hydrogen, you know what's the crazy thing is? It emits a light particle called a photon. And if you were to measure the energy of this photon, is exactly 13.6 electron volts, which I think is amazing, right? That is literally amazing. And because of this emission of the photon, right? So because of this emission of this photon, the bound system goes to a lower energy state. You know what? I should say mass energy state, which is quite surprising. So that really tells you that if you have a stable system, that's exactly what happens. So I think relativity does a really nice job of, for the first time, really telling us what this mass energy expression is, which you got to admit, I mean, it seems kind of obvious that if you look at classical physics, there's this law called conservation of mass, right? Conservation of mass. And it was an extremely strong law. In fact, even chemists still use it. And the reason why chemists use it is that you're essentially exchanging electrons for the most part. But when you start to deal with the nuclei, you have to be more careful. And what I mean by that is that you really have to look at the scenario where you're that if you're dealing with big energies like the masses, rest energies of protons and neutrons versus the electrons, it's easier to see how you can do to change the mass energy of a system. Whereas with electrons, they're much, much smaller. Okay, so I want to move on to the next thing here. I want to talk about massless particles. Now, I don't know how you're going to react to this topic, because there's some sections in here that I really dislike, actually. There's some stuff that really bothers me. And the reason why you may feel uneasy about what I'm going to say here is that you got to remember that special relativity can't answer all the questions. If you really want the answer, you really have to move to the general theory of relativity, which special relativity is contained within. So let's go see what you think. So what we want to do here is that clearly classical particles cannot have zero mass. That is truly a relativistic thing. There were no massless particles until special relativity. And what you're finding here is that the way we define mass in classical physics, it's called inertial mass. And I know some of you SOBs are going to be saying like, hey, you know, it's Newton's first law, right? That's the mass of inertia. That's bullshit. Even Newton writes down that the true definition of mass is force divided by the acceleration. Mass, that is the definition of mass. It's, by the way, it's still the definition of mass in relativity too, by the way. It's just that, you know, we look at it slightly different in relativity, but it's still the same type of thing here. So if this is true here, if I have this inertial, if I really have a zero mass particle, then, you know, particle characteristics imply that the kinetic energy of the particle is not equal to zero, and the momentum is not equal to zero if I'm thinking classical physics. So that means here is that if m is equal to zero, kinetic energy is zero, and momentum is zero, and therefore no classical particles can be massless. Because kinetic energy and momentum are particle characteristics. But what about in relativity? It's just not that simple. I'd like to give you an answer that's really, you know, clean. It's just not so clean. And you'll see what I mean, or at least I hope you see what I mean. Well, let's talk about the speed of a particle. So the way we define the speed of a particle, we define the beta function, which tells us that that's how we get it. Now, if you use the definition of momentum and energy in relativity, one way that we can do this is we could write this as gamma mu times c divided by gamma mc squared. And what you're going to find here is that this gives you a value. So if you look at the mass, look what happens to the mass. It cancels out. the fact that the mass cancels out tells you that this is mass independent. So if it's mass independent, then it doesn't really say very much. Now, I mean, we can say this though, from the 4 energy, right? We can write that the 4 energy tells us that it's this here. And then we get sort of like this for massless particles, which then of course tells us what we already knew. So if I do go look at the beta function, then we could say here is that the speed of a massless particle, well, this guy here clearly tells us then that beta, which is PC over E, is just going to tell us that beta has to be 1. So that means here that all massless particles must travel at C. Yeah.
P as gamma MV.
Yeah, I did that.
Okay, now what about M?
Well, there's an M right there.
Nice.
So I'm not really sure what you're asking.
Yeah. Skirt. Okay, M is in the denominator as well. Like, you know, I was prepared to convince myself that if P is gamma MV and M is 0, that PC over E has to be 0, but you're showing us now that E energy is also a function of mass.
Yes.
I'm tripping, and as it cancels.
No. But by the way, you are not alone. I have trouble with what I'm going to say right now. Okay, I have trouble, and you'll see. But let me continue on to show you where I have my trouble, and then Jason, maybe you may understand, and you can help me figure it out because I haven't been able to figure out this shit in years.
See what I can do for you.
Yeah, I hope so. Okay, so now check this out. So now, I mean, the total energy gives me something completely unsettling as well. So now, let's look at the total energy. So when you look at the total energy, we agree that if we have a massive particle, what it really tells me here is it says that if I look in the limit as U goes to C, and I'm looking at the total energy of this particle, and remember, I typically wouldn't use gamma mc squared as my energy, but I'm just trying to stay real strict here to our definitions here. Then this tells me that this is going to be 1 minus u squared c squared square root, and I'm going to get mc squared, and clearly as u goes towards c tells me that this limit of the total energy goes to infinity. No surprise. And we've already talked about this, that if I look at the impulse momentum theorem, or if I look at the work energy theorem, that if I try to take a particle to the speed of light, I'm fighting gamma the whole way. That's what this is essentially telling me again. But look what happens if I have a massless particle. Oh man. So if I have a massless particle, what am I really seeing here? Well, there's really 2 simultaneous limits going on, right? There's U equal going towards C, and at the same time, the mass is going to 0. That's what we mean by a massless particle. So if I take the limit of the same thing now, you know, we could say that m is going to 0 faster than that, but it doesn't really matter. When we talk about convergence, well, it does converge because essentially I get 0 over 0, or I could go to delta. And what you're seeing here is that this is well defined, but what does this say about massless particles? It doesn't do shit for you. You're in this position going like, God damn it, tell me something that I can wrap my brain around, and relativity is not helping you. So again, I ask the simple question, right? I'm asking a simple question. How can light have momentum without mass? Right? How can light have momentum with mass? You look at relativity, well, one relationship's mass independent. Then the other relationship just tells me that it's 0 over 0. It's not helping me. So here's where, light, how can I say this? Well, clearly, to answer this question, light, right, does carry energy and momentum. Right? How could it come from the sun to us? How can we get a sunburn if it didn't carry light and momentum? And what we typically think about it is that the way I would say this, that in relativity, only the four energy can answer this question. And when I look at the four energy, this is what I mean here. What it says here is that light has energy via its momentum. But we got to be careful when we say momentum, right? What we really mean by momentum is we mean PC, which is really kinetic energy, right? We typically say momentum, but it's really PC, despite not having mass. So when I look at the four energy, we've been saying for some time now that this means that it has what? No mass potential energy, right? No mass potential. And that this guy is just pure kinetic energy. But there's a lot of confusion, right? And the reason why I think there's a lot of confusion here is that the reason why there is so much confusion on this topic is because momentum what do I mean by that? Well, this momentum, it is the definition of momentum, right? This guy here, this is our definition. And what you find here is that this is really not an appropriate definition for momentum. And the reason why it's not an appropriate definition for momentum, because in the limit as m goes to 0 and u goes to c of momentum, we get something that's really, how do I say this? It gives us an indeterminate form here, right? So you get an indeterminate. Do I want to say it this way? Yeah, it's indeterminate. And what I mean by that is that when you look at this thing, we get a value that reads 0 over 0. Right? But this is not equal to E over C. Do you see the problem here? Let me state this slightly different to make sure that you're seeing it. So earlier, we saw that beta was equal to what? 1 when you got P over C. This implies here that for massless particles, I should get this. And at the same time, we also saw that if I take the limit of U, going to C and M going to 0, for P, what we got here was 0 over 0.
Okay. All right. Thanks a lot for calling.
Not the same. So that momentum definition is not a very good definition for momentum. And it causes a lot of problems. So this gets resolved in the general theory of relativity. And what I mean by that, you deal with something called the energy momentum tensor. And when you deal with that, it actually solves all these problems. But it's beyond the scope of this course. But if you're going to yourself and going like, God damn it, what's going on with this thing? I'm just letting you know, there's a goddamn good reason why you should be going like, I don't know what's really going on. Because you could see how these two definitions really hurt you here. But the only thing we could say at the end is what we know what? Massless particles must always travel at the speed of light. Okay? And they still conserve energy and momentum just like anything else. And so, with that being the case here, I want to go in and I want to go look at this example with massless particles, assuming that I can get that example out here. So let's go look at this example. Okay. So this is example 2.4. It says an electron-positron pair combined as positronium. And positronium is this crazy, man, I love this thing. So I would say that positronium is pretty wild. Is this weird shit. Wait, am I spelling? No, I'm not spelling weird right. How else do you spell weird? Something like this. This stuff is weird. because what they do here is that they create an electron. Okay, let's say that this is the electron. And then somewhere else, by the way, this is all in vacuum, of course, right? So this is a vacuum, and here's a vacuum. And then they somehow sneak a positron. So this is an electron, and this is the antimatter of an electron. And this electron is called a positron. And so what you find here is that because these guys are positively charged, in a very weird way, they form a bound state. And if you know anything about quantum mechanics, they produce spectral lines. And you can look at the spectral lines as these things move from energy levels. And then eventually, you can't keep them separated for a long time. And then what happens? These guys annihilate each other. As they annihilate each other, then they shoot off in opposite directions. So that means one goes in one direction and one goes in the other direction. So in other words, I have one photon going that direction and one photon going in that direction. And this kind of makes sense here because what you're finding here is that it has to do this because when you form this positron, it's pretty much at rest. So we look at the momentum, the initial momentum, and it's 0. So that has to equal the final momentum. So that means when I look at this thing, that means that the momentum of one of these photons has to be in that direction, and the momentum of the other photon has to be in the other direction. And so that means you're literally saying that the momentum of the first photon and the momentum of the second photon, they have to go back to back. But the question is, what are the energies of the photons? So the question, what is the energy of the photons? Well, we clearly are doing what? We're converting, in this case, really mass. What do I mean by mass? That means these electrons don't have kinetic energy. They only have rest energy. So you're really converting mass into kinetic energy. Let me be careful. Pure kinetic energy, because they're massless particles here. And so what you're seeing here, that if I look at this thing, then if I have back-to-back photons, what am I actually seeing here? Well, what happens here from conservation of energy, right? Why am I using conservation of energy? Because I have a system of particles. That means then the energy initially must be the energy of the system afterwards. And clearly, if this thing, right, it has to be rest energy of the electron and positron. They have the exact same mass. And then afterwards, they have this pure kinetic energy. But if it's pure kinetic energy, this really means that since they have equal and opposite momentums, then the energy implies that this guy should be exactly the same, where these guys have to be the same. So therefore, it's the same as one of these kinetic energies of these guys. So then that implies here that when I look at this thing here, that means that the total energies of these photons here, right? So remember, this is also the energy of the photons. So then the energy of both photons then has to be the energies of this guy right here. And if you compute that, then that means that this is going to be 2 times 0.511 times 10 to the 6 electron volts. And if you look at this, this is going to be 1.022 times 10 to the 6 electron volts, or 1.022 times mega electron volts. And that's what the energies of the photons should be here. Now, if I want the energy of one photon, then I have to divide that by 2. And another thing that's really, it should be of no surprise here. So what if I have ortho positronium? That means it produces 3 photons instead of 2. So then that means that the energy, so let me be careful here, just to make sure that we're clear in our language here. This implies here that the single energy of photons is then going to be half of the energy of the total energy of these guys. So if I look at B and it says, what if I have ortho positronium, which means that you're doing what? You're decaying. When it decays, that you now get, you're getting 3 photons that are coming out when they decay. And so what happens then is that I get 3. So instead of having it 1/2, it's now 1/3 the energy of these guys. Okay. Let me move on here. This is the last topic in this chapter, a useful invariant and particle production. We've talked about the invariant mass of a particle. Okay, so we've talked about the invariant mass of a particle. And what we really said when we did this, we said that if I have a single particle, that I can look at its 4 energy in any frame I want to look at. So I could look at it from the prime frame, or I could look at it from the unprime frame. This guy is always an invariant. What you're going to find here is that we can also talk about the invariant mass of a system. And what I mean by
There's a
that,
square on the C, it should be a 4.
yeah, thank you. And what you find here is that if I look at a system of particles, then that means, let's say that I have 2 particles, then in a very analogous way, I can form my energy term minus my kinetic energy term. Let me be more careful. How about if I have a multiple particle system? Then I could come in and I can write the momentums of the system too. And this guy here is defined as s squared. And this is called the invariant mass of the system. And this is a very powerful one. It's actually one of many invariants along this way. And I probably won't talk about it, but there are other invariants that are called u squared, t squared, and it depends on how you look at the interaction. And so this implies here that since this is an invariant, all observers must measure this. That's what it means to be an invariant. So it turns out that the most useful for particle production is looking at two specific frames. So for particle production, in accelerators, it's these two frames that are most useful. You don't have to pick these two frames, but it's the two most useful frames. And it's that the lab frame, and the lab frame is the frame that people actually that people can actually design accelerators with. But for calculational purposes, we also pay attention to the center of mass. So these guys are invariant, and they must look at this thing. So what this means here is that if I look in the lab frame, it looks like this. And then you have this guy right here. So these guys must be the same. So by the way, I should highlight this because this is super important. It makes certain calculations just lines, actually. And what you find here is that, here's what you find. So what you find here, if I have a complicated system, so suppose we have E1. Now let me be more careful here. Suppose we have a system. So I throw a glob of something. And let's say that this is my red glob, this is my green glob. And we'll call this 1 and we'll call this 2. And because of mass energy conversion, what you find here is that I can get a series of globs that come out of the system here. And so let's say that this is my picture right here. Well, the beauty of this thing here is that maybe this is 3, 4, 5, 6. Well, if you look at energy and momentum, they must both be conserved. So if I look at energy and momentum, it means this, that E1 plus E2 must equal E3, E4, E5, E6. And momentums can also have to be like this. That must be true right there, right? That must be true. So what you find here is that the center of mass calculation is very, very particular, okay? And what you find here, let me see if I can get something for you. Damn, I forgot to set this up. I wanted to show you an app, and it may not be, you may know this already, but I'm gonna assume that you don't. Let me see if I can get this up and running. Okay, so let me go and show you something here. So if you're in the center of mass frame for momentum, here is an applet that I'm trying to show you right here. And what you're seeing in this applet is that, are you guys seeing this applet right now?
It's really small, but we can see it.
Let me see if I could bring this up bigger.
Yeah.
Is that better?
Yeah.
Okay, maybe that's a, so what you're seeing in this applet here is that this X right here is the center of mass. So you could imagine that I'm standing right on top of the X. So if I'm standing right on top of the X and both of these guys are coming towards me, note that the red is moving to the right and the blue is moving to the left. So what do I see? If I'm in the center of mass location, that means that the total momentum of the system must be zero if they're moving at the same speeds. So if I come in here, look how X doesn't change. And so what you're seeing here is that the momentum at the center of mass, regardless of how many particles you have, will always be zero. I know that was a very simple one, but my point here is this, that if I stand here, okay, so if my observer is right here at the center of mass location, this tells me that the momentum, that the total momentum of the center of mass will always be zero for a two-particle system. But check this out. If I go to a complicated system with four particles, by the way, if you had a four-particle collision like this, that happens like this, are you guys seeing my screen? Guess what? It's an unsolvable problem. You cannot solve a 2 to 4 particle system. You cannot. It's not possible to solve in closed form. But here's what you find here. There's tricks that you can do. And the trick is, if I now stand at the center of mass location, right? If I now stand at the center of mass location, you know what's crazy? The total momentum at the center of mass is still zero. All of the particles are moving towards you, and then afterwards, all of the particles are moving away. So what you find here is that even though I wrote this like this for the kinematic invariant, what you find here is that we play a trick. So the way we do here is that we choose the frame where it's easiest to calculate momentums. So in this picture right here, in the lab frame, we picked P1 plus P2. But note, after the collision, because it's so bad, because there's four particles, this is equal to P1 plus P2, but it's also equal to P3, P4, P5, P6. Why? Because energy and momentum must be conserved. So what do? We come over here and we just say, okay, when we look at the center of mass location, we're going to look at this when it's more complicated. So when you do that, look what you write. Well, in this case, I'm going to have energy of 1, 2 squared, plus, then I write the momentum vectors per 2. And then when I look at the center of mass frame for 3, 4, 5, and 6, I do write 3, 4, 5, 6 squared. And then when I look at the momentum particles, because this is the center of mass frame, you're seeing here that this total momentum now in the center of mass is 0. So I don't have to account for anything else but these guys right here. So that is powerful. And so now it turns out that it's typically the momentum that we're using. This is much easier to solve now. And that's the idea right there. So I want to be really careful with our language here, because there's some really funny things when it comes down to, what's going on here. And here's what I mean by this. These kinematic invariants are useful for many calculations. In fact, most of the problems that you do with this when you're dealing with interactions, decay results, they can actually be solved using this technique. The one problem here that you might get into, though, is that the algebra can increase even more so. It can get horrendous. And you really gotta be, so for some of these problems, if you try to do it this way, well, good luck to you. I'm just gonna go like, yeah, I'm gonna look at that mess and I'm gonna go like, damn, do I really wanna read that? Let me just start giving partial credit here and there, go like, oh yeah, you didn't get the right answer, but yeah, I'm gonna fake my way as I grade through because I don't wanna read that shit. But it is extremely useful for finding minimum energy interactions. So they're useful for many calculations, but are best for calculating minimum kinetic energies of particles. And sometimes they call this the reaction, what do they call it? I always forget that. The minimum reaction energy or something like that. I can't remember. And so what we want to do here, so this would be, what do they call it? I'm stuck on this. It's the minimum threshold energy. And that's a very common name. But remember, you could use it for many different situations. And so my case in point here, when you're looking at this threshold energy, was the discovery of the antiproton. Okay. So as an example, let's talk about the discovery of the antiproton. So when you look at the discovery of the antiproton, I mean, it first started off around 1930 by Dirac, and Dirac predicted that there was antiparticles. And as soon as he predicted it and somebody found the anti-electron, the positron, then they said it must be true for all particles. And that's exactly what started happening. But it's not so simple. Like the photon, there's no such thing as an antiphoton because the antiphoton is the same as a photon. So you have to look at, again, quantum mechanics to really answer the question here. So as soon as they found that anti-electron, the positron, then the hunt for the antiproton was hot in pursuit. It just wasn't so easy. They figured out they found the positron pretty early on in the 1930s, but the antiproton was much, much, much harder. And it took probably another 20 years to find it. And here's what they ended up doing here. They knew theoretically that if you take one proton and you make it interact with the second one. So you had a projectile, and at this time they didn't know how to shoot two particles simultaneously. And then this guy was a target. And what they did here is they took these protons and they shot it into a vat of liquid hydrogen. So what they found here is that if this was the case here, you would produce from this collision 4 new protons with one of these protons. So the P bar means antiproton. That this had to be the case, that you would have to do that. So the question is that, how do you do this thing here? Well, picture-wise, what you're seeing here is that you have an accelerator. Okay, and in this accelerator, what you're going to do here is that you're literally accelerating a proton down the beam tube. Okay, so you got this proton here that you're accelerating down this tube. And then what you find here is that as you accelerate this thing, right, this starts from rest. And then afterwards, what you find here is that this now has some minimum kinetic energy. So this guy's coming through this thing. So the question is, how much kinetic energy does this have? And this is my proton P1. And what you find here is that they shoot it at a vat. So this is a vat of liquid hydrogen. And what you find here in this vat, right, of liquid hydrogen, you're finding that you have a series of protons. But we're only interested in one proton. Okay? It's this guy. And what you're going to do here is that this proton is P2. So when we look at this decay right here, not decay, but reaction, we're really talking about that P2 right there. So if you hit that P2, are you going to get the energy that you're going to get here? Well, here's what you find. The way they actually did the calculation, I think they started around 1945. So the initial calculation was around 1945. The actual experiment, so the building of accelerator plus detector took about 10 years. And by the way, that's always the case. It takes about 10 years. It's almost, think about a power plant. You want to build a power plant from scratch, it's about 10 years. You want to build an accelerator, it's about 10 years. So the initial calculation, guess what they did? They used to get the minimum kinetic energy that that particle had to have in order to produce this reaction. So here we go. So if you do that, we kind of already have our picture right here, right? That's our picture right here. So if that's our picture, what I really mean here is that I'm going to have what? I'm going to have a proton coming in, right? And this proton I'm going to call P1, and it's going to have some minimum kinetic energy K1. So as it comes in, what's it going to do? It's going to strike my blue proton, and as it strikes, and that's what I'm going to call P2. And then afterwards, right? Afterwards, I'm going to get fourth thing that comes out of hitting that one proton. By the way, there's a beautiful, beautiful, beautiful experimental discussion. You got to track which proton you hit in the vat, which is pretty phenomenal when you think about that. Experimentalists are really badasses when they do that kind of stuff. And so what you're going to find here is that you have these guys, and then you have one antiproton. So that means that these guys are all moving away like this, and this is our antiproton. So I have these guys right here. And so what do? In this case, I'm going to stand at the center of mass location. And when you do that, I then get my invariant. So in this case, the momentums are easier for this. And in this case, the momentums are harder. So then I pick the harder case when I look at this. So then I start to do the calculation. So if I start to do the calculation, then I know that this guy here is going to have momentum 1. This guy only has rest energy. And then these guys in this frame will have what? P3, P4, P5, P6. All of these have 0 momentums. And then all of these will have the same rest energy, which should be the rest energy of the proton. So that's the mass of proton. So all of a sudden, the algebra gets considerably easier. So if I write this down, this is going to be E1, E2 squared minus P1 plus P2. But note, this guy's 0. Because it's at rest, that means its momentum is 0. And then if I look at the right side here, well, all of these energies and then all of these momentums we see that all of these momentums are 0 and that these are all rest energies. So what you're finding here is that you get E1, because that's at rest, I'm going to get the rest energy of E2. It's just because it's just sitting there. And then I get that for particle 1. And then afterwards, I'm going to get what? 4 mass of the proton squared. So all I need to do then is that I need to go in and I need to now solve for P1C, which I'm going to have to do later.